Alright, here we have Unit 3, Lecture 2, or Lecture 3.2 as I call it, which is over quadratic functions. For those of you following along in the book, this corresponds to Section 5.1 from the textbook, if you're following along in the textbook. And the topic here is quadratic functions. Now, the last lecture was over linear functions, which are degree 1, just x to the first power there. A quadratic is degree 2. You see the x squared, or a squaring of the x variable in a quadratic function, and that is the highest power. And there's no funny business, no division by a variable, no roots, no absolute values, nothing like that. Just a good old-fashioned degree 2 polynomial. And when you graph a quadratic function, you will get a parabola. Now let's go ahead and briefly discuss the components of a parabola. The first and most important component of any parabola is the vertex. The vertex is the highest or lowest point of the parabola. So if we look at this visual example, that's our vertex right there, is at that point. Now, it depends on which way your parabola opens. You can have a parabola that opens up or a parabola that opens down. If it opens upwards, then the vertex will be your lowest point. If it opens down, let me do a quick little doodle here. If you have a parabola like that that opens downward, then your vertex would be the highest point. Now, the axis of symmetry is just the vertical line that bisects the parabola. So the axis of symmetry will always pass through the vertex. And then the x-intercepts and y-intercepts, those are self-explanatory. X-intercepts are where the parabola crosses the x-axis. Y-intercepts are where it crosses the y-axis. For a quadratic function, you will always have exactly one y-intercept. X-intercepts, you could have 0 x-intercepts, 1 x-intercept, or 2 x-intercepts are possible, depending again if your parabola opens up, down, and where it's positioned. Now there's two ways we can represent a quadratic function. The first we're going to say is called vertex form. Vertex form looks like this. We'll discuss this in detail very shortly. Standard form looks like this, and we'll discuss this towards the end of the lecture. But let's go ahead and open up with that vertex form. So vertex form is what you see here. It's basically you get vertex form by doing a process called completing the square. Now it's called vertex form because these constants h and k represent the vertex of the parabola. So that's pretty awesome. You can immediately identify the vertex when the function is in vertex form. It's right there in front of you. Now, there's a third constant, which we call alpha or a. If a is positive, the parabola opens up. If a is negative, it opens down. So a is just that leading coefficient. So let's go ahead and look at some examples. Now, it's very important that you note in the vertex form, the h is opposite sign. Notice in the formula we see minus h, and the x-coordinate of the vertex is positive h. So the x-coordinate is going to be the opposite of what we see. So the vertex is at 3, not negative 3, comma, negative 12. And if you punch this in, it should work. Right? If I plug in 3, I should get negative 12. Well, 3 minus 3 is 0. 0 minus 12 is indeed negative 12. And if you know the vertex, then you immediately know the axis of symmetry. It's just going to be the vertical line that goes through the vertex, so it's just going to be x equals whatever the x-coordinate of the vertex is. In this case, x equals 3. Now the x-intercepts, we solved these in the last unit. What we need to do is set y equal to 0. So for the x-intercepts, we're going to set that y value equal to 0 and solve. So the trick for solving this is we're going to go ahead and use the square root property. Since all unknown values are inside of a squared expression, we'll begin by adding 12 to both sides, dividing by 3, and then we'll go ahead and take the square root on both sides, just to remember the plus or minus. So you have plus or minus 2 equals x minus 3, so therefore x equals 3 plus or minus 2. So our x-intercepts are at 5 and 1. Yeah. And then our y-intercept, you set the x to 0. So we'll do that over here. So that's where x equals 0. So when you do that, you get y equals 3 times 0 minus 3, quantity squared minus 12. So that's going to be 27 minus 12, which is 15. So there's our y-intercept. And then just pay attention to directions. Here it didn't say we need to write the intercepts as ordered pairs, so it's okay to just write the corresponding coordinates. But if it wanted them as ordered pairs, make sure you write them as ordered pairs. Alright, let's go and look at a second example. So our vertex is going to be at negative 5. Remember, the x value would be the opposite of what you see in there. Negative 10. So that's the awesome part about the vertex, is you get the vertex with very little effort. And if you know the vertex, then you already know the axis of symmetry. It's going to be x equals whatever the x coordinate of the vertex is. Now, x-intercepts, those will take a little bit of work. So let's go ahead and take a peek at that. So for our x-intercepts, we set the y equal to 0 and solve. So add 10 to both sides. Divide by negative 2. Take the square root. Remember the plus or minus. And something interesting happens here. We get plus or minus I root 5 equals x plus 5. We get imaginary x-intercepts. Well, that means there are no x-intercepts. So that tells us this parabola will never touch the x-axis. Well, that kind of makes sense when you look at the vertex. Like if I do a quick little sketch here, negative 5, negative 10, that's somewhere down here. And notice the a value is negative, right? It's negative out front. So this parabola is opening downward, something like that. Well, if it's down at negative 5, negative 10 and opening down, it's never going to touch that x-axis. And we see that in the algebra when we go to solve for it, we get a complex solution. So there are no x-intercepts here. The y-intercepts, let's go ahead and do that. So y-intercept, you set x equal to 0 and simplify. And you're going to get, let's see here, 25, negative 50, negative 60 as your y-intercept. Alright, so that is an introduction to vertex form. And vertex form is the preferred form, particularly when you want to write a function for a parabola described or depicted. So if we look at this parabola, we want to come up with an equation for it. We'll default to vertex form, which I'm writing right now. And our goal is to figure out these three constants. Once we know these three constants, we are good to go. Beginning with the vertex. So we'll start with the vertex. Now the vertex is at negative 1, negative 2. Okay, so that means we can now move on to the a constant out front, or the leading coefficient. So if we look at our incomplete equation, we have y equals a times x plus 1. That plus 1 is very important. Remember, the x coordinate of the vertex is going to be the opposite of what you see there, minus 2. So that's incomplete because we are missing that leading coefficient. Well, it's going to be the same exact strategy as in the previous lecture. What you want to go ahead and do is plug in a point, and plug in any point so long as it's not the vertex. Right, if you plug in the vertex, that x coordinate is going to zero out the first term. We don't want that. So plug in any point off the parabola so long as it's not the vertex. I'll go ahead and plug this point in at 1, 0. So we know the y value is 0 when the x value is 1. Let's go ahead and solve that. So we get 0 equals 4a minus 2. Therefore, a equals 2/4, which reduces to 1/2. So there's our function. So we know the a value is 1/2. Then we have plus 1 minus 2 as our vertex. And if you want to check your work here, you can take any point off that parabola, plug it in, and it'll work. So number 2 is going to be very similar. We start by figuring out the vertex. Once we know the vertex, we can figure out the a constant. So the vertex we get just by knowledge of the English language, so that's provided. So if we were to go and write the function or equation, it would look like this. Remember, so notice it's -5, therefore plus 5, plus 11, so 11 is positive. It's incomplete because we're missing that a constant, so you go ahead and plug in a point. As long as it's not the vertex, it'll work. It says it passes through 0, 2, so we know the y value is 2 when the x value is function. Plug in the vertex, that x coordinate is going to zero out the first term. We don't want that. So plug in any point on. So number 2 is going to be very similar. We start by figuring out the vertex. Once we know the vertex, we can figure out the a constant. So the vertex we get just by knowledge of the English language, so that's provided. So if we were to go and write the function or equation, it will look like this. Remember, so notice it's -5, therefore plus 5, plus 11, so 11 is positive. It's incomplete because we're missing that a constant, so you go ahead and plug in a point. As long as it's not the vertex, it'll work. It says it passes through 0, 2, so we know the y value is 2 when the x value is 0. So we get 2 equals 25a plus 11, so 2 minus 11 is -9 divided by 25. -9 25ths is our leading coefficient. So this parabola opens down. And if we want to write the function, that would be our a constant, -9 over 25, times the quantity x plus 5 squared plus 11. Cool beans. Well, that's vertex form. So vertex form displays the vertex. The only thing you have to keep in mind is that the x coordinate of that vertex is going to be the opposite of what you see in the structure. And vertex form is preferred, and it's great for modeling. So if we want to model some quadratic graph or some description, we can default to vertex form, in which case all we need to do is figure out the vertex and then plug in a point to solve for that leading coefficient. But there's one more form to discuss, and that is standard form. So let us look at standard form. So if you want to convert from vertex form to standard form, you just need to multiply everything out. If you want to convert from standard form to vertex form, you would need to use a process called completing the square. But we're going to go in and study standard form. Now, guys, it's still a parabola, right? And if we're talking about a parabola, the most important piece of information is its vertex. So its vertex is going to be at -b over 2a. That's the x coordinate of the vertex. And once you know the x coordinate of the vertex, you can just plug it in to get the y coordinate of the vertex. So this standard form takes a little bit of work to figure out the vertex. So the vertex is going to be at -b over 2a, and then you take that number and plug it back into the function to get the corresponding output, i.e. y value. So in this case, -b over 2a is going to be positive 10 divided by 2 times 1, which gets us 5. Now we don't stop here. We got to take that 5 and now plug it in. And when we plug that in, that's going to be 5 squared minus 10 times 5 minus 24. And that's going to be 25 minus. And we get -49. So -49. So our vertex, the x coordinate is 5, the y coordinate is -49. And there's our axis of symmetry. Now the x-intercepts, we do the same as before. We set the y to 0 and solve accordingly. So this is a little bit of a refresher from the first exam. We'll go ahead and factor that. That'll factor to 12 and 2. 12 x plus 2. So that tells us our x-intercepts are at 12 and negative 2. And then for the y-intercept, we set the x to 0. So that would be y equals 0 squared minus 10 times 0 minus 24, which is negative 24. Alright, there's all the information about our for parabola. So if you want it, you can go ahead and graph it with this information. Let's look at one more example, at least of this type. So we want to figure out the vertex of this parabola given by negative x squared plus 6x plus 10. So it's the vertex x coordinate is given by negative b over 2a. So that's a negative 6 over 2 times negative 1, which is going to get us 3. And then we go ahead and plug 3 back in. So let's go ahead and do that right quick. Let's say negative 9 plus, and we get 19. So our vertex is at 3, 19. And axis symmetry is x equals 3. Now I know x-intercepts are going to exist because it's negative out front and the vertex is at 319. So it starts at 319 opening down, which guarantees 2 x-intercepts. So to do that, we're going to have to solve this equation, setting the y value to 0. Now unfortunately, this is not easy to factor, so we're going to go ahead and use the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Alright, so I'm going to go ahead and pull out my calculator and compute that. So just be very careful with your signs. There are a lot of negatives in play. So stand by for one moment. So the first, and I'll go ahead and round it to 2 decimal places. First value I'm getting is 7.36. The second one, let me go ahead and compute that. So it'll be negative 6 plus that value. Second value we get negative 1.36. So we got 7.36 as our first, and negative 1.36 as the other. And then the y-intercept, again, you just set the x to 0. That'd be negative 0 squared plus 6 times 0 plus 10, which is just going to be 10. Alright, so to summarize with standard form, if everything's all multiplied out, you have to remember the vertex is going to be located at negative b over 2a. That's the key there. So let's wrap up with an application, a diving example. If you've taken a physics class, you've seen these quadratic functions extensively. So here, the height of a diver jumping off of a high dive is given by that function, where h is a function of t, h representing height, t representing time. So how long will he be in flight? Well, he's in flight until his height hits 0. So we set height equal to 0 and solve. Alright, so this is clearly not going to be easy to factor. So what we need to do is go ahead and run our quadratic formula. So time equals negative b plus or minus the square root of b squared, being, which is 49, minus 4 times a times c all over 2a. So good review of the quadratic formula going back to the first test. So let's go ahead and punch that into the calculator. Alright. And what we get is 1.10 is one answer. And let me see here. We can take negative 7 and add that value. and then divide accordingly. And for the second one, we get negative 0.88. Alright, so there's only one answer that makes sense here. It's 1.10. And I didn't write it earlier, but the unit of time is in seconds. So 1.10 seconds. Alright, so that tells us how long this individual will be in flight. Now, what will his height be at 1.5 seconds? Well, we know he's going to be in flight for 1.1 seconds, so actually this is a bit of a trick question. The diver will already be in the water. That's because we know flight time is 1.10 seconds. So we don't have to do anything there. If you plug in 1.5, you're actually going to get a negative number, which doesn't make sense. And the reason you get a negative number is because in part A, we figured out the flight time. It's 1.1, so the diver will not be in flight at 1.5 seconds. Their flight will have been concluded by that point. Now the diver will have some peak height that is worth knowing. We want to know what's the highest point they're at. So the highest point, or peak height, well, what's the peak of any parabola? Well, that would be the vertex. So the key to figuring this out is by determining the vertex. You'll notice it's in standard form. So let's go ahead and compute the vertex. So it's at negative b over 2a, which is negative 7 over 2 times negative 32. So it's going to be basically 7 divided by 64, which there's our x value. So that's around 0.11 seconds. And then if we go ahead and plug that in, we go ahead and plug in, so that would be function h at 7/64. If we plug that in, let's go ahead and do that. So let's punch that value in. We get 31.38. So that's the peak height and time. So the highest this diver is going to be is 31.38 feet above the ground, and the diver will reach that height at 0.11 seconds after flight. So basically you got a diver who's barely jumping off the edge, right? They give a little tiny baby hop and they're over the edge. So naturally, if you're barely jumping off the edge, then you're going to hit that peak height very quickly, if not almost immediately, which is what we see here. Alright, so here we have our final example, and we are done with quadratic functions. There's a supplemental lecture you're welcome to watch, but you are now ready to take the quiz and to tackle the worksheet. So feel free to begin both and have a wonderful day.